Hello, and welcome everyone to today's webinar, part 3 of our SPaT webinar series, and the second webinar in the series focusing on design considerations for SPaT deployment. The SPaT webinar series kicked off in March with part 1 focusing on SPaT challenge activities and part 2 also focusing on design for SPaT deployments. Both of these webinars are available using the links to the bottom right of your screen. As a reminder, the National Operations Center of Excellence is designed to offer resources and support the TSMO Transportation Systems Management and Operations community. Feel free to browse the entire collection of NOCO resources in our Knowledge Center and subscribe on our website for our newsletter and major TSMO announcements. The links are shared with you in the Useful Links box on the right side of the screen. For this and every webinar, a recorded version of the webinar, along with the presentation slides, will be available 24 to 48 hours in the on-demand learning section of our website. We will have a question and answer session at the end of the webinar, so if you have any questions, we encourage all of you to enter them in the questions pane at any time. The questions will be read out loud, one at a time, and our presenters will answer each question. This is a quick overview of the agenda for today's webinar. We'll have Blaine Leonard from Blaine Leonard from Utah DOT do a little bit of additional welcome and introductions. Then we'll have David Kelly from Subcarrier Systems Corporation talking about the map messages in a little bit more detail. Chuck Felice will take over from there to give some information on Utah DOT's map message creation strategy. And then finally, Greg Larson from Caltrans will talk about vehicle position correction needs and solutions before I bring it back at the end with the Q&A portion for the webinar. With that, I'm going to hand it over to Blaine Leonard of the Utah DOT to get us started. So Blaine, go ahead.
Great. Thank you, Steve. Appreciate that. And I would like to add my welcome to everyone who's joined today. It looks like we have just over 100 people with us today and some additional people adding. So thank you for being here, and we hope this is a useful webinar for you. The webinar, as Steve indicated, is focused on map messages. Map messages are a really important part of broadcasting SPaT and map at an intersection. And as we've discovered, creating that map message is not trivial, and there's a lot of pieces to it to make sure that it's done right and done well. And so I want to add my appreciation to David and Chuck and Greg today for taking the time to prepare some presentations for all of you to walk through the ways to do this. There are multiple ways to create map messages. I will also add that there is a map message creator tool that FHWA has created and developed, and it'll be referred to a couple of times today, but not talked about in detail. But there's an upcoming webinar next week that will do that, and I'll show you that in just a second. So I'm sure everyone knows the SPaT challenge is a challenge to all of us who are infrastructure owners and operators to deploy DSRC infrastructure to broadcast SPaT and map messages in at least one corridor in every state by 2020. The SPaT challenge is 2 years old. It was initiated on April 20th in 2016. So just a few days from now is the SPaT challenge birthday. And in the last couple of years, we've had a huge amount of interest, and we now have 35 locations in about 25 states that are done deploying or in the process of deploying. From what we can tell, it looks like we have about 500 RSUs up and operating in those places that have blue pins on our map, and another 2,300 roadside units planned for deployment in these other places that are shown on the map. Frankly, we know of 300 or 400 more RSUs that are being planned or deployed in places that aren't shown on our map. But we see this as great momentum, and we're excited about it, and we're excited that all of you are excited about getting involved in connected vehicle deployment. We've had a couple of webinars before this one, and some of you have participated in those. The first one introduced the SPaT challenge in sort of a broad way and talked about systems engineering and model concept of operations, a little bit about cost procurement and selecting corridors. The second one, which was the first one focusing on design considerations, really focused pretty heavily on the SPaT message and how you get the SPaT message put together. We introduced the V2I Hub, which is a product also developed by the US DOT, and talked a little bit about some agencies that had deployed onboard units to receive the SPaT message. These are, as Steve mentioned, archived for video and the presentations themselves, and you can find them here on the SPaT Challenge research page at the National Operations Center of Excellence in the spot there where I show the blue arrow, and you can download those, and in a few days you can download today's as well. That's also where you can register for the subsequent ones. If you are logged in today and you're working on the SPaT Challenge or planning to work on the SPaT Challenge and don't show up on our map, please go to this part of the page and give us a little information so we can get you on the map. It's important that everybody knows what's going on and that we see the momentum visually on the map, and so please do that and give us information about what you're trying to do. So we have another couple of webinars coming up, as I mentioned a few minutes ago. Next week, on the 24th, we'll have a full webinar dedicated to the Map Creator tool, which will be a live demonstration of how that tool works. And some of you will find this to be a useful way of creating maps. And then on May 15th, we'll go to part 3 of our design considerations. And then finally on June 12th, we'll talk about deployment and validation of the message. So hopefully those are on your calendar and you've registered for those events. With that, I've got the wrong slides here somehow. With that, I'll turn this over to David, and David can talk to us about the map message and what it is. Take it away, David.
Lane, I thank you for the introduction, and congratulations on the 2-year birthday. I'll start with a little bit of ancient history and then pick up. We've only got about 15 minutes for this, and this could very easily be a half-day seminar that might be more suited to someone trying to develop tools to create maps, which limits the audience to Leidos and about a dozen other companies. But my goal today is to teach you what's in a map and why it's there. It may seem a little complicated, but we've made it as simple as we possibly can, and it links to the SPaT, and you just literally cannot have one without the other. I'll go over some of the basics of how the encoding works. Because of the presence of tools, most of you never have to dig into the depth of ASN1 details, but just about anything you're going to come across. In fact, I'd say 990 out of 1,000 maps is capable of being represented, and therefore there's some complexity that might not be there or evident why we chose it that way. But we'll go through a couple of the most typical use cases that come up. We'll explain a concept called connects to, which is how the lanes in the map intersection are connected to the signal phase movements in the signal controller by way of the SPaT. Then pedestrian crossings are very popular. We'll spend a little bit of time on that, recap putting it all together, and give a little pragmatic advice, because today no tool does entirely what is wanted, and all tools are growing in terms of their ability. And there's ways to test a good map. There's some ways not to test a good map. Finally, I've got 2 pages of resources, because to understand the map process, you've got to have civil engineering skills, message set skills, and a fair amount of GIS skills, and that's a pretty tough combination. So starting right away, maps and SPaTs, one doesn't exist without the other. SPaTs do represent the movements and the phases and the time on the wall when those movements will end. Patrick misspoke a little bit about phase 1 SPaT. It's always been a series of what are called time marks rather than type countdown timers. What happened between the 2009 copy and the current copy is we could only estimate a phase a minute ahead, and various people with fixed timing said they wanted more, so now you can estimate a phase 30 minutes ahead. But otherwise, the basic principle of modulo time is the same. When they're used together, all maps and SPaTs fit in a PSID called intersection safety. The map is also used for things beyond intersections, although that's a relatively immature area in the DSRC message set. The plan is all roadways, temporary roadworks, incident management, close a lane and trim some trees. It will all be represented with map primitives. Right now the message section only got 15 messages in it, and map is used for mostly intersections, but like I said, has great growth potential. Things we won't cover today are requesting a preemption and priority and how you understand the general status of a signal once you've asked for that priority. Right now we are working on a recommended practices document. It will be called 49/10. That will deal with a pragmatic advice for maps and SPaTs and clean up a few minor things we found. A similar document called /11, chaired by Larry Head, will be dealing with preemption and priority issues. Now I'd like to show you a typical map. Oops, I think I've lost a slide. I lost the slide. No, it's a forward in a moment. My mistake. Sorry to get out of sync. Let's start with the basics. What's in a map? Well, a map is not an intersection. It's as many as 32 intersections, although everything done today has been one intersection. Within each of those 32 intersections are a collection of lanes. Everything done in the map is in a simple orthogonal XYZ system. It translates from the elliptical system of the Earth, of latitudes and longitudes, to a flat orthogonal system. Maps support a 1 centimeter resolution, which just happens to be about 1/10 of 1 microdegree. It's 101 centimeters in one direction and about 80 to 89 in the others. How you convert to that is a technical issue that tools like Leidos will do for you. Resources in the back have further links. Maps are transmitted as compressed messages. DSRC does not have a lot of bandwidth. So rather than giving lat-long points of every little point, what you're given is the offset in terms of centimeters from the last point. It's an important thing to understand. You've got to flatten a map before you use it. They're not, unlike BSMs, usable right out of the box. And it's pretty easy to put a BSM on a map. You just subtract the anchor point of the map and translate the resulting deltas into centimeters by multiplying twice, and you're there. Now, for SPaTs, it's a little bit different. SPaTs represent one or more intersections. It can be as many as 4, and again, there's only been 1. Each intersection can have a number of active movements. All reds are not transmitted. You can transmit them, but that's not a best practice. Of the 32 possible active movements, each movement has a pile of times. Those times are how you tell when the light will change and what it will change to. This supports not only classic signal stuff, but eco-driving, where you can tell a vehicle expect a green in 37 seconds, and he can manage his power. And there's some dithering in there if you don't want people jumping the light on you. Another concept about SPaT is it holds more than just the intersection. It holds which lanes are currently active and which regulatory rules are in place. If you've got, for example, speed zones that vary with the school day, or lanes that are parking at one time of the day and not another time of the day, that time information is in SPaT. SPaT is a dynamic message. Maps are essentially static messages. Now I'd like to show you a map. I've shown you a map with polygons drawn from the 2009 version of the standard that was deployed in Anthem before the MITS work. You're seeing some BSM vehicles plotted on top of it. I believe that's Larry Head driving, to be honest. This was where an early test facility was put up and has been kept up. Most people don't have a tool like this, but it's pretty simple to take maps, render them into polygons, put a BSM on it, and then gain some useful feedback. But you can also look at this map, and we could look at this in detail, but we haven't the time, and you'll see gaps. You'll see areas where the edges of the stop lines don't align. You'll see a number of attributes, if you're familiar with that area, like curbs and medians and crosswalks with places that would be ADA handicapped problematic that are not on the map. And that was some of the stuff that was addressed in the 2016. That is the I'm going to go into details of what's in a map and how it's constructed. Basically, a map is nothing but a pile of lanes. All the lanes are generically similar, as opposed to the 2009 copy where there was a lot of hierarchy and it made it difficult to write the software. There are 8 basic types of lanes. From the point of view of the map, a pedestrian lane and a motor vehicle lane just have different flags set in their header. There are also things like bicycle lanes, trains for tracked vehicles, and medians. Medians can be important to describe if you're trying to support public safety that might cross over them. Medians can be important if you're going to route your buses along the median for high density use, which is a project just starting up in San Diego. Each lane type then has the attributes you need to describe it. For example, audio-visual clues for ADA crossing of a pedestrian crosswalk make no sense for a motor vehicle lane, and vice versa. And then within each lane, there are a series of nodes. Nodes are how the lanes are described. And at each node and between each node can be attributes. I'll come back to that. The attribute system is relatively complex and allows you to add new things. We knew when we were building this that new attributes were going to come out of the woodwork. So it's possible to add regional attributes. Oh, that's another minor point. Patrick said a region meant a country. It's purposefully ill-defined in SAE. And the use case is a country could be the North Americas or Santa Monica. Those were always the two examples given. But anybody can add regional content in a particular way and still meet the conformance requirements of the SAE standard. This was designed to provide a means for people to experiment but still be valid, still be interoperable, and also provide a means for the committee to say, well, look, it's been deployed, people liked it, now let's move it from regional into the full standard. A couple of more things about the generic lane. Every lane has default values. Think of it like a style sheet. Within the intersection, there is a section that says what's the default lane width. If you're using common design properties, that's the only time you have to describe the width of the lane, or if it differs. One of the things we talked about this morning in the SPaT task force meetings was we probably will expand that to have a default lane for sidewalks. They hardly ever follow the same design geometry as the road. Inside the lane, we've got a series of nodes. Nodes, again, are just offsets. I'll show that on the next slide. At the top of each lane are a number of attributes. Amongst the attributes are the maneuvers that you can make at the stop sign or stop line. Here I've shown a variety of graphical maneuvers, but the 186 countries that drive on what we call the wrong side of the road have parallel versions. For example, you can make a U-turn on the right. It's in the standard. You wouldn't deploy that in North America. Okay, going a little bit further for how the polygons of lanes are described, rather than describe four corners and points, we describe center lines and widths. So a simple two-node point intersection, which is what many of you may start with for your first intersections, is simply the center of the stop line and about 300 meters back and whatever your width is. However, you can modify that with a lot of different attributes. One of the most common is a sense of skew. Stop lines are rarely ever a perfect 90 degrees, and when lanes stack up to each other, you need that skew to know if you've got a line violation. And finally, on this slide, from one point to another is a filleting process. The points simply project, and you get a nice clean polygon. A little bit of math, but nothing. Everybody on this phone call survived high school, so you're all familiar and could relearn it if you had to. A little bit more about generic lane attributes. Attributes are things that live either at a specific node or between a specific node. The attribute system in the Leidos tool and every other tool I've ever seen is still very, very weak. It's because it really didn't exist in 2009 when that tool was architected. Or in our tools either. But attributes basically allow you to state something from from one point to another. The classic example is a do not block. A do not block might also have a stop line at the other end of the do not block, another attribute. A good example for an attribute that's localized to a node rather than spanning one would be a curb at a crosswalk. If the curb is not canted but it has a step off, that's an ADA concern to some people. You may care to encode that. Finally, we need to talk about the all-important connects to. Every lane has a stop line. Well, most lanes have a stop line. And every lane with a stop line has a connects to, where a variety of connections, notice that it says you have 16, tells you what it connects to and which signal group it is. And the signal group is how you connect it back to the movement phase. There's some other useful information here, and you notice that maneuver is dotted here. That indicates it's optional. It's not necessarily appropriate to tell everybody where every lane goes, but it allows that provision. Now I'm going to talk about multiple lane use. Harkening back to what I said before, maps are static. Maps are static, SPaTs are dynamic. So if you look at this right on red sign here, and you notice it's placarded for certain days and times, it's the responsibility of the SPaT to tell you when that is active, because the SPaT knows what time it is. The way this is implemented in the map message is there are two essentially identical lanes, and the allowed maneuvers at the stop line for one of them permit the right on red and prohibit the right on red in the other lane. We use this trick for reversible lanes, time of day parking, right on reds, any other crossing regulations that will vary with time. And the key thing to know here is that SPaTs are more than just signal controller states as a result of that. Okay, so I'm going to go through a connects to example, and this would do better with animation, but I wasn't sure how far we could push it. So allow me, when I move my mouse, do people see those? I guess they do not.
No, I don't think so, David.
Okay. On the lower left is a lane with a forward arrow to the right and a black line indicating the stop line. Let's presume that this is a left turn and through lane, and it has these attributes. No U-turns allowed, a left is allowed, and a movement ahead is allowed. No U-turn with the X there. If the map doesn't say you can do it, you can't do it. That's why I drew it a little bit differently. So in this example, no U-turn would be allowed. And you'd want to look at the signal heads and the signal light, and therefore in map SPaT EEs, the signal group ID, to tell when you were allowed to go to the left turn lane. Now if we look at this classic doghouse here, you'll notice those words are a little different. Those are the words that the international traffic engineers, some American representatives, some Australian, British, and many European representatives came up with as the most, for lack of a politically correct phrase, gender-neutral way we could explain what we meant. You'll have to look into the standard. In fact, we very specifically tried to avoid using colors. Some countries have things like flash on green before you can go, and those are in there as well, although we don't use them in America. So when you get the protected movement to the left, it's going to come from one group ID, and you might make that left-hand turn. When you get that green admissive ball, you can move ahead, but of course it's not protected. And that's going to come from a different group ID. If you were the vehicle sitting at that stop line, you would know what lane you're in, and therefore what connects to match to you, and therefore which of these groups matches to you. And my footnote here is worthy of mention too. New York's done both this and a different pattern. Not all maps have to be self-contained. It's a pattern of the map design that you might describe the ingress lanes in one message and the egress lanes in another intersection, in another map. So just a real quick pedestrian crossing example. Typically pedestrian crossings are just two-point nodes that are put about a meter or more in to the sidewalk. Scrambles are supported. You can do the lines if you want to. I'm told that some scrambles after football games in Michigan don't even pay attention to the lines. It's just a mass movement. You can do that as well. Crosswalks are a little bit odd in that they've got some ADA issues. For example, a median jutting into the walkway can be very problematic if you're in a wheelchair and force you to go outside of the safe zone. So things like that are in there as well. It's very common to have tapers. I'm not aware of the perfect intersection that goes left and right and up and down, but tapers most often come up with crosswalks. Here is a crosswalk in the New York deployment. You can see the taper on the top. This is dealt with changing the width and changing the end taper. And complex geometry like that requires some skill in the GIS tool. But otherwise, it's in the map, and with time, these tools will all grow to be able to support it better. So coming down to a summing up point, your typical map has one intersection with many lanes. In each lane is a group ID. Typical SPaT has one intersection, transmits the active movements, each one of which has time marks. And the time marks, again, are wall clock when the things will change. And those are connected to the group ID. The group ID is the link between the two of them. These guys live in a PSID called Safety App. Signal request and intersection collision aren't covered. There's also a message called intersection safety or intersection collision message. That's basically a BSM repeat to tell other people that something bad is about to happen. And if you need help plotting BSMs on the map, if this doesn't make sense, drop me a line and I'll show you how to do it in a little more technical detail. Now, I'm going to very quickly conclude these sections because we've got another speaker to talk about it, but the normal way to build a map is to gather source maps, translate those source maps to WGS84, not state plane coordinates, not NAD27, not, God forbid, Google coordinates. Then you capture that into some kind of GIS tool, typically in JSON or KML. You avoid ASN1 as long as you can. You add these lane attributes, and then you reduce it to ASN1. And then you can QC the work to make sure the lanes don't overlap each other or leave huge gaps. And I see I left a comment to myself there that needed to be removed. So a good map has the following features. It's essentially self-contained accuracy should be a decimeter. Its connection to some sort of truth, that is WGS84, ought to be better than a half a meter, and you really need to have very few gaps between the lanes. What usually happens with the BSM algorithm to put it in a lane is you take the center point of the BSM and you embiggen it, yes, that's a Simpsons reference, to the size of the vehicle, and then try to place it with a center of gravity mentality into the correct lane. It's also important to have some traceability. You're not going to do this map once. You're going to keep updating it as conditions change. So you need to know how you created it, what the source map was, what the frame of reference was, how the coordinations took place. Chances are that unless you're using GPS, you're not getting WGS84, so there's some translation from a state repertoire of maps. Then a couple more slides here. There is an official PSID that you should use for this. There's also a range of test IDs that SAE has arranged with IEEE that you can use. There is a range of intersection numbers that we didn't have time to go into, but there's a chunk for an experimental range. Those make a good place to start. Numbering practices are all being developed by SAE now, and they'll end up in the /10. They will be recommended practices, not normative. It's common that you need corrections at the intersection because that's the moment you're trying to figure out when a vehicle is at the stop line or when it's going to exceed past the stop line. And you've got some design choices, one of which is just who's signing the messages. That continues to be up in the air with different architectures being proposed. Finally, if you find there's something you need, it can be added in the local content, in the regional content, and just call. We'll show you how to do it. Because if you felt you needed it, maybe somebody else does. So on behalf of the SAE committee, we want to know about it to try to include it. Then I've got a couple of resources here. I won't show those on the screen for long. You can acquire the standard from SAE. I put it in an XML image if you want it. These three have to deal with datums and lat long issues. And basically, these are some of the tools that were used in the graphics. All but one of these is openly available and free. And the final thing is some commentary we're putting together that is still very draft, but it's supposed to answer the how do I do this kind of questions. I think at this point, I turn this over to Chuck, but I'm not sure what to push. Thank you. All yours, Chuck.
Okay. So, David, thank you very much for that presentation. It described a lot of the things that I do when I'm creating maps, and it kind of gave me a little bit of good feelings that I'm doing some of these things correctly. So what I want to talk about is how we create the workflow in creating map messages, map data for our projects in UDOT. So we're using MITS software. And for those on the call that are not familiar with MITS, Multimodal Intelligent Traffic Signal System, and it
in this case, we're using the traffic signal priority portion of MITS. And MITS was designed and created by Larry Head, a professor at the University of Arizona. And for the MITS, for TSP, we're broadcasting SPaT map information. We're also sending SRM messages and SSM messages. So we currently have DSRC deployed on an 11-mile-long corridor in Salt Lake City along Redwood Road. And we've got 30 intersections, 25 of them have DSRCs. And the goal of this was to improve the bus that's running on this route from 86% on time to 94%. So I created the map data for these 25 intersections. So what is the Nmap file? So when we took over the MIT software from Larry Head, and we were porting it across, the map data that's required by MITS is in an Nmap file. And what I learned last February when we had the National Conference of Excellence, or Center of Excellence, in Salt Lake City for a meeting, Larry described that the Nmap file came from DARPA Robotics back in the 80s, I think, when they were testing robotic vehicles. And there was really no other standard for putting map data that he could find, so he used the Nmap format. So that's been carried along with MITS. And it's an ASCII text file that has all the information in it that David mentioned in his presentation. Our map file, when we take that and our MITS software reads it, we put it in the March 2016 release of the J2735 standard. So in our map file, Nmap file, we have intersection information, identification, the attributes, a reference point. I'm going to go through these kind of quickly because David covered these. Approach information. And approach information is kind of giving way to more of lane information instead of approaches. But we decided not to change our Nmap file to meet the new standard. We're just going to take what we have, and we have the MIT software make that translation into the proper J2735 format. So again, here are more components of it. David mentioned the traffic lane information, lane IDs, lane types, the attributes, which are bit field definitions, of course the lane width, number of nodes, lane node coordinates, number of connected lanes, and of course connected lane identifiers. So how did I go about creating these map files? These are the tools that I used. I use Esri, ArcMap, to put all my node points in. On that map, we have 6-inch photography from Google that is obtained from the State of Utah's Automated Geographic Resource Center. I have to pull that information out of ArcMap, put it into Microsoft Excel, add more information in for the attribute information that's required for the Nmap file. I do this through Notepad++ editor. I found that I was having line feed carriage return issues if I used the normal Notepad or other editors, and this one worked the best. And then I wrote an Nmap file parser that validates the Nmap file that I created. And I did this because in the beginning when we started this project, I would create Nmap files, and it's such a manual process that there could be some errors introduced. And the Nmap file parser, and I was handing these files off to our contractor who was reading this in the field, and they come back and say, something isn't right here. So now I validate my maps before I give them off to our contractor. So the workflow, and David kind of had that in one of his slides, so I'm going to give it to you the way we do it at UDOT. I go through and I create road intersection reference points and lane nodes in ArcMap using that Google imagery. And the question that we had is, when I'm creating these coordinate points, how accurate are they? So I created a few intersections, and Blaine Leonard, who sits right next to me, hired a survey crew to go out and take the coordinates that I created and verify them. And we found out that they were right on the numbers. There was one intersection they found that I was off, and I determined that I was using old imagery. And when I got the correct imagery in, corrected it, no problem. So in our case, ArcMap and Google Imagery worked just fine for getting the accuracy that we needed. So once I have the nodes in, I export that reference point and lane node data into a Microsoft Excel spreadsheet. At that point, I add additional information that's required for the Nmap file. Then that data is transferred to the actual ASCII Nmap file, and that's where I'm editing it, making sure it's in the format that our MIT software requires. Again, after I'm done with that, I validate it, run it through my parser, looks great, and then I send that off for use. Very manual intensive process that would love to see improved, because I don't want to spend all my time doing data entry for the rest of my life. So here's an example of an Esri ArcMap for one of the intersections on Redwood Road. And you can see the node points that I've dropped in there. I've got the reference point at the center of the intersection. We labeled these based on lanes, the point in the lane, and how many node points are in that lane. Such as on one of these east legs, you see lane 1.1.1 is one of the node points. You go back, it's 1.1.2, and follow that nomenclature. I export the data to the Excel spreadsheet, and you can see here I've got my lane node information, the coordinates for those points, and then here's your connected lanes that David mentioned. So in this case, lane 1.1.1 connects to two lanes, 6.1, which is straight, and 8.1, which is a right turn. It's an approach, not an egress. The lane attributes, you can see that field, that's a bitmap. And each one of those bits determines, as David mentioned, is U-turn allowed? Can you do a right turn, a left turn, protected left turn? I have lane IDs that are used, lane width. So all that information is what is needed to go in the Nmap file. Here's the example of the lane attribute bit field definitions. And I had a really hard time getting this information. When I first started this process, a year and a half ago, 2 years ago, just trying to track down what these bits were and how they're defined. And it was kind of like the Rosetta Stone. Once I got the document I needed, then I could just move forward with it. So I created a spreadsheet where I had my definitions preset, so it would be very simple for me to go take that information. Here is the Nmap file in Notepad++, the editor. And you can see the information, and this is a human-readable form, so it's very easy to go back and check to see if I got everything. And this is what I validate through my file parser to make sure everything's great. And then here's just another view of it, of what all this information looks like. And this is the kind of information that David described as far as what is required when a map data payload is created for sending across DSRC. Here's just what my output looks like from my validation. I go through and check all sorts of things, making sure lanes aren't missed, things match up, many checks. Here's an example of a small road intersection. This is one I showed earlier, where we don't have a lot of lanes, so not too bad to do. Here's an intersection that probably had about 26 lanes, maybe to 30. So this comes into the size of the intersection is an issue because the 1,300 bytes that are allowed in the map data payload comes into play. And when we first started doing this, we were exceeding that number. And one of the reasons we exceeded it is because we were using full coordinates, latitude and longitudes. We don't use offsets. So what are some of the lessons learned? Well, based on the experience I had over going and doing these intersections and doing them a number of times, because, again, we exceeded the 1,300 bytes. The other question is, how many node points should I put in a lane? Do I need them every 70 feet, every 100 feet? Do I need one just at the start of the lane and the end of the lane? What about a curve? How many points do I need so that the chord drawn between points does not go into another lane? So documentation is really needed. I spent a lot of time trying to find out information. I searched the web about the Nmap file, where the attribute fields are, again, the load, the number of nodes, other little gotchas that kind of would bite me when I wasn't expecting it. One of the things that would really help for someone creating map information is what's the best practices manual for creating map data. And I know David mentioned in his some of the documentation that's coming along, and this would be wonderful if you could have this kind of information at your fingertips when you're dropping in these points to document what the intersection geometry is. The second item I mentioned, again, 1,300 bytes. Knocking down the node points helped. We also found that the UPER data compression really helped a lot. But we have larger intersections coming along, and I'm looking at going from absolute coordinates to offsets. The manual process could be speeded up by using software to automate some of the tasks in creating this Nmap file. In our case, we're looking at, do I bury a lot of that information in an Esri shapefile instead of creating that intermediate spreadsheet, and then we just have software that would read that shapefile and from that shapefile create either the Nmap file or directly create the binary information that's required for the map data packet. So I want to talk about intersections that are under construction. On the Redwood Road corridor that we had, I didn't have too much of a problem because the intersections were all done. I had a few intersections where I had old photography imagery that the intersections were old intersections, and I was able to get new photography that cleared that up. But we have a project going on in Provo, Utah right now for a bus rapid transit project. We got 47 intersections. They're going to have DSRC. The corridor is 12 miles long, 3 to 9 lanes per intersection. We're using Econolite Cobalt controllers. We've got full fiber connectivity, and again, the goal is to be at 97%. The problem that I have with this corridor, and here's a picture of the corridor, the 11 miles of it, is that some of these intersections, this is what the photography looks like. The road's ripped up. So where are the lanes? Where am I supposed to put the node points? So in this case, we have plan sets that have this information. And so I can go and get this, but yet it's not on my imagery. I can't overlay this. So I went back to the contractor, and they have this information in MicroStation. And we were able to convert MicroStation into KML files, and then the KML I could bring into ArcMap. And when I did this in this case, we found out there was a little bit of discrepancy in what their coordinates were when they did the conversions. But in ArcMap, I'm able to kind of nudge their layer over and get it to where it needs to be. But again, getting this information from the right people and determining what do I do when I don't have good photography is, now that I have this overlay, that's what I'm using to create my node points. So what are the future needs based on my experience of banging my head on the wall or finding something that really makes my job easier? So again, best practices guide for collecting intersection geometry would be wonderful. Best practice guide for creating the map data. Some methodology for automating getting this map data created. And I went back in February when we had the meetings here in Salt Lake. Chris Stanley, who's going to be presenting next week, and he's from Leidos, gave a great presentation on the FHWA Map Creator tool that will be presented next week. And a lot of things would make my life a whole lot easier being able to use that tool. But some of the issues is I would be using the same imagery that I have or the imagery that they have in their app. And in this case, I still had roads that were ripped up. And we mentioned to Chris some of the issues and enhancements we would like to the system. And one is, can we overlay plan sets on there, like I did, so that I can actually drop my points in. Their tool would, you drop the points in, you enter information, and it creates the binary information that's required. So that could eliminate a number of my steps. The other thing that you need is validation of the map message data. And David mentioned this a little bit, and I know in Chris's tool they have that, or they're working on it, that when you create this, you have to make sure that what you created is proper, so that when we hand this off to our people who are using this map data, it's not going to break the software or they're getting bad information. And one attribute that we really like about the map file is that it's human readable, because if you've looked at that 2735 standard, it can be pretty daunting when you start looking at all the information of what's supposed to go in there and the binary information. And having this ASCII file, when you need to go back and look at it, you can determine, oh, something's wrong here, or this binary value isn't correct, maybe an attribute. So either dumping out, once the payload is created, if it also create maybe an XML or a JSON file, that you could read that, if necessary, to determine if things are kind of screwy. And the Nmap file, in my opinion, and also Larry had kind of agreed with this in February, is kind of an old technology, and it really should be disappearing. And I'm hoping that as new tools are created, where David had mentioned, many of these tools are coming along, that this could replace a lot of this manual process that has been taking place. Blaine mentioned in the start of this webinar that there are many ways to create map data, and there are. It's just we need to find ways that are efficient and handle cases where you don't have good information or your imagery, it doesn't match what's really on the road. And once we can figure out those kind of oddball cases, I think a tool would be wonderful to have. Computer vision is another one. And that's where we kind of need to move with map data creation. And here's some of the documents that I referenced. And I think that's it. And I'll hand it off to Greg Larson.
Thanks, Chuck. So my name is Greg Larson. I'm a researcher at Caltrans, which is also known as the California Department of Transportation. And I want to caveat my presentation today by saying that I am not the subject matter expert on this topic. Unfortunately, Dr. Kun Zhao of the California PATH program at UC Berkeley and Professor Matt Barth at UC Riverside's College of Engineering Center for Environmental Research and Technology were not available. They are the subject matter experts. I have a breadth of knowledge and I understand the concepts of this topic, but I do not have the depth of knowledge that they have, and I'm certain that there are many folks on the phone who know more about this topic than me. But having said that, let's move along. So I'm going to start out by talking a little bit about GPS in general, and I think many people on the call probably understand GPS and how it works. I'm going to follow up that with some discussion about the different ways there are of correcting position, and then talk a little bit about our test bed in California that we're using to do some experiments with this topic, and then finally a little bit about the onboard units. But to jump into the background, the map message is broadcast to the vehicles, and the vehicles use that to enable applications both for safety and mobility. And in order to make use of the map, they need to know where they are very accurately for many applications with lane level precision. And so what we're going to talk about today is corrections to the GPS signal that they are getting in the vehicle already that enable them to get that lane level positioning in a way that's continuous, reliable, and accurate. Because GPS, as you'll see in the following slides does not always have those characteristics. And we mentioned RTCM. Just for your information, RTCM stands for Radio Technical Commission for Maritime Services. So it's a standards development organization that's primarily related to maritime, but it does provide a mechanism that the auto industry has been using to correct the positioning they're getting from their local GPS to give them lane level positioning accuracy. And we would be broadcasting this correction to the vehicles using DSRC. So just to give you a little bit of information about how GPS works, is a constellation of 31 satellites, at least operated by the United States, that are orbiting the Earth. The satellites are transmitting a signal, and they're about their position and their time, and a GPS receiver needs to pick up at least 4 of those satellites, and ideally with a geometry that can give them an accurate position, as you'll see in the next slide. But you see satellites can locate you on a sphere and then a circle and then 2 places on Earth, and then finally the 4th satellite gives you the exact location. So with basic GPS service, without any kind of enhancements or augmentation, 95% of the time you will be within about 10 meters of accuracy. You could be as low as 5 depending on the geometry of the satellite constellation, or as far away as 40 meters from where your position is located or is shown. And there are a number of factors that can affect the accuracy of your data. And you can see one of the items is the geometry. When the satellites are spread out but not too far spread out, you get good positioning. When they are clustered together, you are not as accurate. And then finally, multipath. If the signal from the satellite is bouncing off objects on the Earth before it's being received by your GPS receiver, then it can also impact the accuracy that you get from the GPS. And there's a link here that shows you that talks about that effect. There's different ways of improving the accuracy of GPS. One of the most rudimentary is differential GPS. So you have a base station at a known location. It's usually a high accuracy base station, and it knows the position, its own position, and is sending a correction message to roving GPS. A lot of applications for example, surveying and agriculture are using this type of correction. There's also real-time kinematic, and as we go through, I'll be talking about the RTK method that we're using in our test bed to correct position. One of the ways of getting the RTCM correction is through a protocol called NTRIP, Network Transport of RTCM via Internet Protocol. And it is a protocol for streaming the position correction over the Internet in accordance with the standards that have been developed by RTCM. So you see in this diagram, there is an architecture that includes the sources, which would be the base stations that are transmitting their data to servers. And then those are in turn sent to casters that can broadcast that correction to local clients. And again, there's a reference to more information on this. It is an open standard, and there is software available for free that can enable you to take advantage of this service. So the current standard for RTCM is 104.03.x, and it defines message structures for the real-time kinematic applications and supports GPS and GLONASS, which is the Russian version of GPS. The messages are in 3 different types, and you need to get at least one message from each of those types. One category is observations, another is station coordinates, and finally antenna descriptions. And the next slide describes these. And actually, I'm going to click once more. So that you see the 3 groups: observation, station coordinates, and antenna descriptions, and the message types. For the application that we have in mind, the minimum is type 1002, which has carrier-based requirements. Then on station attributes, you need to know the antenna reference position, and then finally an antenna descriptor as a minimum requirement. And you'll see that in the testing that we've done, we are actually using a higher standard than that. But it's important to note that within these message groups, the higher the number, the larger the data size. So there are balance. There's a trade-off for using the higher accuracy. You see here there is accommodation for RTCM within the SAJ2735 message frame, and it requires the interrupt client that I mentioned earlier. There are 2 options for doing this, and I'll talk about both of these. One is to use the roadside units built-in application, and the roadside units typically have that. They may not be capable of supporting the latest version of RTCM. A second is to host the client on a separate processor, which is the way that we have done this. And you see on the right side of this slide the ASN.1 syntax for RTCM. In order to broadcast RTCM, you need to identify a nearby base station, preferably within 50 kilometers, and that supports the current standard. You need to create an account, and in many cases, you can find a service that's free. I know within California, because of the earthquakes we have here, there are a large number of Ntrip casters that are available for free service. And I know in other places, for example, Minnesota, because of their agricultural needs, has a number of free services that are available. And I think in different parts of the country, it's not that difficult to find a nearby free source of RTCM corrections. You need to set up the streaming service or streaming system on a computer that can act as a server and the Ntrip caster. There's README instructions, and once you start it up, it's pretty much set it and forget it. You really don't need to know that much about Ntrip or the standard itself or even the SAE message set in order to make this work. So I talked about 2 options. The first is to take advantage of firmware that's built into the RSUs. Again, the potential downside of this is that the firmware may not be up to date. The RTCM standard is a living thing, and it has changed in the recent past. The second option is to host it on a separate processor, which is the way we've done it in our MITS application, similar to what Chuck described in Utah. So you can click on this link to get the Ntrip client, and then create the software that you need within your separate processor to support it. So we, again, use this option because it gives us better control of the sources of data. Now, I'll talk a little bit about our testbed. For those of you familiar with the area, this is located in Palo Alto. The upper left corner is the southeast corner of Stanford University, just to give you a perspective of where we're at. The green dots are the current up and operational intersections. Red dots are the ones that we're planning on adding to the corridor soon. It's about a little over 2 miles long. Right now it has 11 intersections. Carries about 50,000 vehicles per day, so it's a fairly busy arterial. And it is running the MITS applications, including ISIG, which is Adaptive Traffic Signal Control, and the two signal priorities for transit and for freight, as well as a pedestrian safety application for crossing. You see on the right side of this slide a photo of the installation. There's two DSRC antennas out on the signal mast arm, and the top box in this photo is the current Savari radio. The bottom box is an older Denso radio that was used initially. So the radio's on the mast and the antennas are on the mast arm. Currently there's 11 intersections. By the end of this spring we'll have 17. Currently the roadside units are complying with version 3.1 of the FHWA spec, and we will be converting to version 4.1. The MITS roadside processor uses these versions of Linux that are shown here, and we're broadcasting the map message, the SPaT message, signal status message, and RTCM from the intersection in accordance with the 2016 version of J2735, which is the latest. We do not have the luxury of the fiber that the lucky folks in Utah have, so we are using a wireless backhaul using 4G and LTE. And you see the website here for the test bed, and you can look at the real-time health, see which radios are up and running and how many BSMs they're receiving, how many SPaT and map messages they sent out, as well as additional information if you have an interest in taking a look. These are the messages, and again, for broadcast from the RSU, we are sending the map message, signal phase and timing, signal status message, and RTCM corrections. And vehicles that are equipped can receive the basic safety, or will broadcast the basic safety message and a signal request message for requesting priority, for example, at the intersection. And you see under RTCM, we are using type 4 or type 1004, 1006, and 1008, which again are the higher level of accuracy for RTCM. So as far as the Ntrip server, we are using the nearby Jasper Ridge, which is operated by UC Berkeley and Stanford University. As you can see, it's fairly close to the proximity of the test bed, about 5 miles away. The Ntrip caster is located at the PATH headquarters in Richmond, so there's an internet connection between the Ntrip server and the Ntrip caster at PATH, and then there's a cellular connection back to the individual intersections to give them the information they need to broadcast RTCM. And this is just the architecture, shows the onboard unit and the process we're going through and processing the RTCM correction and getting the improving the position. And then some more, a little bit deeper dive into what's inside. There's DSRC connecting the roadside unit and the onboard unit. Again, the message is encoded in using the standard and broadcast. And then I'm nearly done, but the whole reason for this is, again, lane level positioning, and so it is intended to be received by the onboard unit and then used to correct the position to hopefully get lane level positioning accuracy. One of the problems is that there really isn't, while there is a standard for the roadside units that's maintained by Federal Highway Administration, there is no similar standard for onboard units. And in many cases, they may not be capable of handling the RTCM corrections. And I know that the auto industry obviously has an interest in addressing this challenge and making sure that they will be able to. It's, I think, incumbent upon us to do what we can on the roadside unit side and make it easier for them once they do reach some standards. And one of the things that we're trying to do is do some experiments to determine just how well this this process will work. So we've equipped some vehicles with RTK-enabled GPS and a laptop, and we are doing experiments. And as far as the status, this is my last slide. We've taken a look at what we can get with the wide area augmentation system, and that's providing typically 2 to 5 meter accuracy in open sky conditions. And then we are also working on or planning to do some RTCM version 3 experiments. We have work underway with UC Riverside to do that on both open sky and rural canyon conditions. So that is my last slide. And so I will hand it back to Steve to, I think, handle the Q&A. Thank you for your attention.
Okay. Thank you, Greg, and thanks again to everyone who's been speaking over the last hour or so. It's 3:07 p.m. Eastern Time, so we have a little bit of time here for some Q&A from the audience. If there are any questions, I invite you to please enter those in the question/discussion pod that's viewable in your windows here. But we've got a couple of comments and questions so far, and I'll parse these out to the group, and yeah, we'll get going. So I think the first one, David, you addressed it a little bit in the comments, but it looked like there was some confusion between the 82 hex and the 84 hex PSID, and I wonder if you just want to add a little bit of additional clarification or distinguishing between the two.
Well, for various reasons, ASN1 requires you to use decimals, so I just looked it up in the standard, and it's 130. But in the slides, it says 184, and those that know me know I'm totally dyslexic, so my apologies, that's a typo.
Ah, okay. No problem. So I just wanted to make sure we were able to clarify that to the audience. So next question, and this would just be for anyone in the group, maybe particularly though for Chuck, things you come across, and the others as well, but are there any how-to manuals for creating map files?
No, not that I've found. What I did find in MIT's, Larry Head's team created a field user's guide, and that had information about some of the items that I needed to put in the Nmap file. But again, I had to dig deep to find out what some of those values were that they'd mentioned, and that's why it was kind of difficult to find. And that's why I'm hoping that there can be a best practices manual for creating map files.
May I add to that?
Absolutely, David.
That's what the original intent of the /10 effort was to be, not so much standards, and although we've run into a host of problems, but just a practical how to do it guide. We do have a private website that's run by our company answering some of those questions, but we haven't got any mechanism of funding the effort. And one of the problems is that everybody wants to use a Google map to demonstrate. Google will let you put things up on a website, but they won't let you publish it in an SAE document. So we're struggling, but our goal remains that /10 will have recommended practices, and this online resource will remain agnostic, but be able to point to vendors and point to best practices. And I'm hopeful that a lot of those, just tell me how to do this questions, can be answered on this online site.
Okay, great. Appreciate those insights. The next question, I believe this one is geared towards Greg. Can you provide a ballpark number for RTCM implementation?
Yeah, I'm looking at that question, and I'm not sure, is that dollars?
Do you want me to take that one?
Well, I mean, a ballpark number of what? Because assuming that it's how much extra effort cost is there for RTCM? There's virtually none. There is development of software that on hardware that's already there. So if that's the question, then the answer is almost none. But I'm not sure that is what the question really is.
Well, let's focus on that, and if that didn't address it, and I'll ask the individual who typed that question to come back with some additional clarification. So.
Oh, I want to beg in a little bit more while he types. There are about 100,000 base stations in the world. There are maybe 10,000 N-trip casters. I know that because we happen to provide a free one, so we're familiar with a lot of them. This has become a commodity. It was a very expensive thing for surveyors and agriculture. But in the last 10 years, it has become a commodity. That's the future we need to prepare for here. As Mr. Larson says, it's cheap.
Okay, great. And it looks like, yes, that indeed did answer it, so appreciate the perspective from both of you. The next question, in terms of absolute accuracy requirements for maps, are there thoughts from the group on a top-level threshold?
Let's see here. This is Chuck, and we were within probably half a meter when we went out and field verified the coordinates that I had created, and for us that was good enough for our buses. Now, is it good enough for vehicle to vehicle when you need to apply the brakes? And David, you probably have a little bit more information on this since you helped create the map standard and what you think the accuracy needs to be.
I get that all the time, and I haven't got a definitive answer. Sometimes the Google Map's perfect, sometimes the Google Map's not, and sometimes the Google Map changes. I live on the edge of LA in the mountainous areas, and the minute you hit the mountainous areas, we see a 30-centimeter bias. So these are really rough comments, but try to hold better than better than half a meter. Try to find some sense of absolute accuracy, because what we see is adjacent tiles, regardless of the source, are pretty coherent, but if you can just geo-rectify the whole thing, you're doing pretty good. And make sure that your resulting lanes don't have huge gaps. But I think for the accuracies that we're looking at now, before RTK becomes more prevalent, and presuming that people are using low-end L1 only U-block junk, if we can hold things well under 50 centimeters at the 30 centimeter mark, we've hit the sweet spot of accurate enough without driving up cost. I'm more concerned with cost. Map creation has to become a commodity too, not a $1,000 exercise for an engineer. Right now, I'd rather see more maps with lousier quality, but I don't have a black and white answer to that question.
Okay, any other thoughts from the group? No? Okay. So the next question, I think, Greg, this is actually directed towards you, it says Gary, but with regard to the upcoming comparison between RTCM v3 and differential GPS what ground truth would you use for comparison?
So yeah, this is a detailed question. The UC Riverside researchers are working on this, and I'm not certain what they're using for ground truth. Since they are experts in GPS, I assume they're using a hyper-accurate GPS as the ground truth, but that's mere speculation on my part. And unfortunately, I don't know. We have not received the report back from them on the results of their testing because they're not complete. So I don't know the answer to that question.
Do you want me to fill in practical advice again?
Sure
Please.
thing.
Broadcasting faster than 1 hertz is a diminishing return on investment because the signal doesn't evolve that quickly. There's no real benefit between 1 hertz and 10 hertz. Less than 1 hertz, you start to notice things pretty quickly. These things are all time-stamped, so that the transmission latency really doesn't affect it. People in our office are transmitting stuff from Japan to our office in LA and sending it back. No big deal. That's not the issue. Doesn't mean that half the BSMs are not getting corrections. It means that the way it works in the vehicle is the last correction is simply projected forward in a linear time sense. So it's a good question. It's just not really the root problem for using RTCM. When you've got a fix, you get 100% increase in accuracy. You hold to a couple of centimeters. That presumes that the base station is correctly located. A base station that lies moves you to whatever the base station says. Many of you have heard me say this before. The base station is God. Whatever it says goes. So it's just a question of setup more than anything else.
Okay, great. Thanks, David. Greg, I think this next question is for you as well. For the test bed in California, did you guys need some kind of black box to translate RSU inputs to the controller?
And the answer is yes. And it's complicated. For our setup, we are using a protocol called AB3418, which is not really a standard. It's something that's only available in California. The proper way to do this is the way the folks in Utah have done it. They have a black box between the roadside unit and the traffic signal controller that's based on a Linux industrial computer. And they're using NTCIP as the standard to talk to the controller. So if you're interested in how it should be done, that's the way it should be done. The way we are doing it is peculiar, and we are working as quickly as we can to replace the AB3418 with NTCIP. But our signal controllers don't have software that supports NTCIP, so we're not able to do it the way that Utah is doing it and the way that it should be done. So hopefully, Hassan, that is satisfactory as an answer.
Okay, great. Thanks, Greg. So the next item, just a comment from one individual who states, last time they priced a base station, if there truly is a need, they are in the $20,000 range. Just quick, I don't know if anyone, any of the presenters here have seen, significantly different prices, or if that kind of aligns with your own understanding as well.
Well, and let me jump in quick. As an infrastructure owner-operator, we're not going to put a $20,000 piece of equipment in any of our intersections. That's why this architecture where we take advantage of free services from Ntrip servers and casters is an ideal solution. I know the auto industry, when they're testing, doesn't mind doing that, for a test setup. But if they are looking to us to put that expensive a piece of equipment in an intersection, that's not going to happen.
Hear, hear. This one base station covers, with the type of low-grade automotive junk we're talking about here, junk being a price point, not a pejorative phrase, 25 meters or 25 kilometers or so on a side. Most states have good CORS networks, continuously operating reference stations. Most of those are free. There are exceptions. The existing agricultural and survey needs that your state's already dealing with means you probably have a set of corrections. Reducing this to a translated into ASN1 and just use what you got problem. But base stations can cost anywhere from $5,000 to 50, depending on how many features you want.
Okay. Yeah, it sounds like there's not a pressing need for significant investment in base stations outside of what's already out there. But in the event that there is truly the need, as this individual commented, it's good to know that there's that range. So, okay. So the next question: RTCM Type 1004 broadcasts at 5 hertz, while BSM broadcasts at 10 hertz. Does that mean that half of BSMs are not getting corrections for lats and longs contained in the BSMs?
I thought I tried to answer that one before.
Yeah,
no.
I think you jumped. Yeah, David, you jumped ahead. Shunming, I hope you got the answer that you were looking for.
Oh, yep, you're right.
I think because David answered that earlier.
You did. Sorry about that. Okay, next question is, any thoughts on who is going to maintain the map data down the road via public agency or private services?
This is a really good question because with the map data, I could see, where's that data going to reside? Is it going to be in a DOT's GIS department? What about different cities when they have roads and intersections, signalized intersections? So they have their own data as well. Or can it become a commodity where you have private services going out and collecting it, and then agencies would just buy that data? And I think a lot of this comes down to how easy can map data be created for intersections? Can it be done through a company driving the intersections and collecting that information? Aerial photos, have a company doing that. So, creating the map data is a headache as well right now, but who's going to maintain that data, and where's it going to reside? That's some of the biggest issues that I see. Blaine, you might want to chime in on this because you're more in the management side of this instead of me being a technical.
Thanks, Chuck. Yeah, I think we've got to deal with the issue of how we update these going through time and keeping an eye on what changes happen in the roadway and how we monitor that, how we deal with these. That's something that we've not really given a lot of thought to since we've been so busy just building the maps to start with. We've got to figure that out.
Are there any other thoughts from the group on that question?
This is a future prediction, but I believe we become too concerned with the DSRC ASN1 representation, and I believe moving forward something more like KML or GeoJSON will become the means by which maps are kept and maintained and exchanged with these other parties, regardless of the business model that eventually evolves for whether the state creates it or a private sector creates it, and what the quid pro quo to get your hands on it becomes.
Point. So a related question then, and I suppose depends widely on the ownership and then the method by which the map data is created. What would be a reasonable cost for maintaining map data? Thoughts from the presenters?
That depends.
What does that mean?
Yeah, reasonable cost for maintaining the data, that would, again, that comes down to how is this data being collected? How's it being, how do you maintain it? When we have an intersection that's undergone construction, who's going to go out there and get the information? So is it just through photography? Is it through an intern that you're having do it where it can be cheap? Or do you have a contractor go out and you have a contract with them and they collect that information for you? So what's the cost per intersection? Is it $300, $400, $1,000? Until we find a better way to collect the data and automate the process of creating a map, I don't think you can get a good idea of what it's going to cost to contract that out compared to if, like someone like me who does it. But the problem that I have is, how do I know when an intersection is going under construction? I would have to coordinate with somebody in UDOT in the construction department, telling me that, hey, we've got something going on here, and we're ripping up your intersection. Because right now, I haven't done that because the intersections I have, I already know the people I'm working with, but what about other projects in the state? And as DSRCs are deployed at intersections across the country, this, it kind of goes up exponentially in the sheer numbers, and then how do you maintain those numbers? And that's why I don't know what a correct cost would be until, if a company can come up with a quick way to do this at a reasonable price, it could solve the problem. And that's where we need to find out what's the best methodology for doing this that provides the accuracy we need, because there's still a lot of handwork involved in creating attributes for lanes. It's not just dropping points down, it's knowing what the connected lanes are. So there's hands-on work. How do you automate that so you can make this so you hit a price point that suddenly is reasonable for people, meaning private companies, to do that, or even for a DOT to do that? At least that's my opinion.
I think I completely agree with that, but I'd offer another insight.
Please.
It's got to be, take a look at the current situation where people routinely retime a light. That's a fact of life, and some people have budgets for that. Whatever retiming or resyncing a map would cost has got to be a small fraction of that cost, and that sort of sets an upper bound.
That makes a lot of sense. That's helpful, David. Thanks. Okay, so a couple final questions here. Should there be a systematic assessment for reaccuracy requirements between lower signal priority versus more demanding collision avoidance applications?
So this is Blaine. Yes, I think that's appropriate, and that's why, as Greg described the position correction process, I think it's very appropriate for you to look at the application you're going to run and determine whether that correction is necessary or not. And the higher accuracy, the more demanding applications will require better data, and that would sort of push you into doing that. The same could, I don't know if this question was about maps or position correction, but the same could be said about maps. And I think David said in one of his early slides, don't build a map that contains everything. Build a map containing the things you need. And so you can base that on the particular applications you're looking to run. Now, the risk there is, as automobiles start to show up with applications built onto them, and Toyota announced yesterday they're going to start doing that with DSRC. Have we built maps that are adequate for those applications? And sitting here today, we don't know what those are. So the risk is you could undershoot the target, if you will, and then find ourselves a little bit short. Now, we can always go back and update the map and do those kinds of things. But as we do the analysis, I think we need to be a little forward-thinking about making sure that we're sort of ready for what might come at us.
Let me add an observation regarding this question. We were talking about RTCM corrections at an intersection, and again, DSRC has a relatively small footprint, but for collision avoidance, you're going to need that application anywhere. And it may be, and more likely, it will be outside the range of any RTCM correction. And this is a conversation that we've had with the auto industry. Is right now we're only planning on providing that correction at intersections and maybe some limited other locations, but don't they need it everywhere? And some of the car companies say yes, and some say no. So there is a need to continue exploring what the actual requirement is for GPS accuracy or positioning accuracy everywhere, not just at intersections. So that's just an observation.
So I've got another question, and this one's kind of for David. A follow-up to Blaine's comments is, if I'm driving a car in Chicago and I drive it to Los Angeles, and I'm expecting, and I have DSRC applications running, I'm expecting those DSRC applications to work from state to state. Is there a bare minimum in map data that has been, I know there's required information that's in a map message and optional components. Is the bare minimum good enough for what applications will need?
Without understanding the application, there's no way to answer that.
Yeah, and so how do you plan an intersection to put information out there if you don't know what the application is going to be? And how do we, if automakers are putting applications in their cars, how do we know that, what do we have to do to our systems to get them to work? Do they have to give us information of what's coming down the line, so we have to adjust our map data? I see this as kind of a big issue that as a user, if I'm driving, how do I know if what I have is going to work?
It's a valid question, but I don't think I need to be the ball catcher for that one, because it's cross-cutting, and if we don't communicate with each other, we usually make mistakes. So, not to use that as a straight thing, but that's why we have standards communities that are made up of people that are roadway owner and operators and car makers and infrastructure bits and pieces providers, et cetera, et cetera. They all have a different take on it, and we try as gentlemen to come to a common agreement on what we can do today while not precluding what we hope to do tomorrow. Like I said, it's kind of a stock standards answer. Sorry.
No, that's okay. Thanks, David.
Okay, so I do see some additional questions coming in. Unfortunately, we are over time. We are at 3:32 Eastern Time, so a few minutes past. But if you do have additional questions or want to follow up, you can reach out to us, and we can definitely put you in contact with today's presenters. And also, there's tons of relevant information around this accessible through the SPaT web pages on the NOCO website, as Blaine shared at the very beginning of the webinar. So with that, just a couple of quick wrap-up items. I just wanted to, again, thank you for everyone for attending today's webinar. Wanted to remind you that we have the next webinar in the SPaT series a week from today on April 24th, and that's going to focus on FHWA's map creator tool. That, there was a little bit of allusion to that earlier. Chris Stanley from Leidos, he won't be personally presenting, but he and his group at the Turner Fairbank facility through FHWA have been working very hard to develop this map creator tool. And you'll see some demo for that resource, and hopefully answer some of those questions as well. I wanted to thank our panelists as well. We had some good information here today. A recorded version of this webinar along with the presentation slides will be available on our website in approximately 24 to 48 hours. And then just on behalf of the National Operations Center of Excellence and our presenters, thank you for joining, and have a great rest of your day.